This is a Thunder Physics video about vectors. First, let's look at the difference between vectors and scalars. Vectors are quantities that have both magnitude or size and direction. Scalars are quantities that have magnitude or size only. Now, these refer to physical quantities. So, can you think of some examples of vectors? We'll be learning about velocity. That's a type of vector. We'll be learning about position. And we'll also be learning about displacement. All different types of vectors because they have both magnitude and direction. What about some examples of scalars? Mass is a scalar because it has magnitude but not direction. The same with speed and distance. So you'll notice that these three things, distance, displacement, and position, are very similar, but you need to know the difference between which ones are vectors and which ones are scalars and why that's the case. So all through the school year, make sure you keep track of what are vectors and scalars because there are always multiple choice questions regarding the difference between those two. All right, now notating vectors. This is how you notate or write a vector. Either a bold R or a R with an arrow over it. Because my professor used an R with that kind of arrow, that's the kind of symbol I use for vectors. This is how you draw a vector. Always an arrow. The direction is important, so always include the arrowhead and make sure you label it. So the length determines the magnitude, and whichever way it points determines the direction. And again, this is the tail, and that's the head. All right, now, we're going to use a component addition of vectors technique to solve most of our vector problems. There are 4 steps. The first step is to resolve each vector into x and y components using these equations. Now, we would use 3 sets of these equations, all 3, the A, the B, and the C, if we have 3 vectors. But if we only have 2 vectors, we would only use the A and the B. The A and the B for just 2 vectors. Now what we would do is we would take all the x components, add them together to get what we would call the resultant x, and add all the y components to get what we call the resultant y component. Then we would calculate the magnitude using the Pythagorean theorem. And finally, we need to find the angle. So let's apply all 4 of these steps in an example. So this is a sample vector problem. Let's say we had a vector called vector A that had a length of 15.8 meters and had an angle of 71.6 degrees. And another vector, vector B, that had a length of 25.0 meters at an angle of 126.9 degrees. Let's say we wanted to add vector A to vector B. We always add vectors head to tail. Now this is the equation we would use. We would say literally vector A plus vector B will equal our resultant. That's what we're looking for. Okay. We would never add tail to tail. That would just be wrong in many different ways, if you know what I mean. Now, again, we had vector A that was at 15.8 meters at 71 degrees. Okay, so the first step we want to do is to resolve each vector into its x and y components. So these are the equations we're going to use for vector A. So we plug into vector A using the horizontal equation. So the x component of vector A is A cosine theta. So we take this 15.8 meters, we plug it there into our equation, and we multiply it times the cosine of 71.6 degrees. And that'll get us a certain answer. We do the same thing for the vertical component. So that's the vertical. Here's the horizontal. For the vertical component, what's different, you'll notice, is we're using sine versus cosine. So we plug those in our calculators, and we want to make sure our calculator is in degree mode. Now this, if we plug it into our calculator and do it correctly, our horizontal component turns out to be 5 meters, and that goes there. Our vertical component turns out to be 15 meters, and that goes there. So notice this is the horizontal and vertical components of our original A vector. So this is what we call A sub x, and this is what we call A sub y. Okay. Now let's go back to our B vector. Remember, we said it was 25 meters at 126.9 degrees. Now we're going to use our B equation, which is essentially the same thing as our A equation, but for a different vector. So our 25 meters at 126.9 degrees, we're going to take the cosine of the 126.9 degrees and multiply it times the 25 meters. The same thing in this other side, but in this time for the vertical, we will use the sine function. So likewise, what we end up doing is we end up plugging into those equations. Now notice when we go horizontally for this particular vector, that shows that we're going to the left. And anytime we go to the left or downward, we show a negative sign. In this case, I wanted to make sure you guys understand that the negative sign is redundant because we're already saying we're pointing it to the left. So it's already negative. We really don't have to put that negative sign there if we don't want to. So B sub x ends up being negative 15 meters, and that's that portion right there. B sub y ends up being positive 20 meters, and that ends up being right there. Okay, so notice we're basically, for both the A vector and the B vector, we're making right triangles. Okay, so we said we were going to add the B and the A vector, always head to tail, just like that. Now step 2 is where we add the components. So remember our horizontal components, was negative 15 meters, and that was our B vector, and our A vector's horizontal is 5 meters. So we'll take negative 15 meters and positive 5 meters to get a total of negative 10 meters. Okay, so this is what we call R sub x. Okay, our y component is where we take the vertical components of both of our vectors. In this case, the 20 meters and the 15 meters, and that's how we get 35 meters, or our R sub y. That's called our resultant y or vertical component. Okay, so we add those values up. The x components are negative 15 and 5, so that gives me negative 10 meters. The y components are 20 and 15, and that gives me positive 35 meters. So those are the same values that we had here, what we called R sub x and R sub y. Now, those two vectors make what we call our resultant vectors. They become R sub y and R sub x. Now, this R, that's technically our answer. That's our resultant vector, because remember we said R is equal to A plus B. So these are the vectors that we're actually looking for. That if we find the values for R, then we're done with this problem. So we go on to step 3, in which we use a Pythagorean theorem for our horizontal and our vertical. We plug it right into our Pythagorean theorem, and we find out that the magnitude of our resultant vector is 36.4 meters. But that's just the length, or its magnitude. Because it's a vector, we also need to find its angle. So let's start off by finding this angle here, the angle from what we'll call the negative x-axis. All right? So from the negative x-axis, again, negative x-axis, we would use are this equation where we take the inverse tangent of the opposite side. Remember, SOHCAHTOA means we take the opposite side, 35, and divide it by the adjacent side, take the inverse tangent of it, and that gives us a particular angle. So this angle here, from there to there, from our negative x, is 74.1 degrees. Okay, so it's okay for us to say that the angle is 74.1 degrees above the negative x-axis. Sometimes, however, we're asked for that angle from the positive x. So from the positive x-axis, we would have to take 180 degrees and subtract that 74.1 degrees to get 105.9 degrees. So we can say that our answer, therefore, is 36.4 meters at 105.9 degrees from the positive x-axis, or 36.4 meters at 74.1 degrees above the negative x-axis. So that's how we end up with that answer. All right. So we got our answer of R is equal to A plus B vectors. This is our R vector, our A vector, and our B vector. That's how we got that answer. Now, I just want to review really quickly the different quadrants and how we would find them. So let's say, for example, that we have this vector here. We could say that, just like in our previous angle, that this is 20 degrees above the negative x-axis. Okay? Or we could say it is 180 minus 20 degrees from the positive x-axis, which would be 160 degrees. All right, so that would be from the positive x-axis. Now we've also can look at the third quadrant. So this is the third quadrant. We just did an example of the second quadrant. In the third quadrant, we could say that this is 20 degrees below the negative x-axis. Or we could say it is 180 plus 20 degrees, which would be 200 degrees from the positive x-axis. Okay? Now, over here in the fourth quadrant, we could say that this vector is 20 degrees below the positive x-axis. Okay? Or we could say it's 360 minus 20, or 340 degrees from the positive x-axis. Now, finally in quadrant one is the easiest. If we have something in quadrant one, we just take whatever that angle is and say, like in this example, that it's 20 degrees above the positive x-axis. And there you go. That's our video on vectors.